Hello, my lovelies. Today is April 30th, and our goal is to graph rational functions. Just a couple of quick reminders. If I was able to read all the pages of your summative, your scores are in Student View, and I provided you detailed feedback on Google Classroom. There's still a few of you who I need better pictures from so that I can give you feedback on your work. So check again Google Classroom and Student View to see if I left you comments needing new pictures from you. We've started in the last couple days working on, sorry for that interruption, those were my groceries at the front door. One of the silver linings for me of this whole stay-at-home thing is that I've figured out how to order groceries online and have them delivered to my door. And I really hate the grocery store, so that's a great thing for me. So we've spent the last couple of days just starting to get familiar with direct and inverse variation. And we said that inverse variation was a very basic form of a rational function. So today we're going to get into a little bit more depth on graphing rational functions. So at the end of yesterday, we defined that as where y equals some polynomial. This is almost always just a number. So 1 is the most basic number, but it can be other numbers, and it affects like the tightness of the graph. And then this is a polynomial. This usually is where the variable is, and it has like x minus something or x plus something. So in a rational function, we know that a denominator of a fraction can't equal 0. So whatever would cause the denominator to equal 0 results in an excluded value. So the parent function of a rational function is, the most basic one is f of x equals 1 over x, or y equals 1 over x. And then we make it more complicated by including an h and a k. So I'm wondering if you can guess what the h and the k are going to do. If you've been paying attention to the different types of functions we've been working on, you should have a good guess for that. I put 1 here because that's part of the parent function, but now that I'm looking back at my notes, this might have been better to be an a. So to recognize that it doesn't have to be 1. So I'm going to put an a there. Think of like all of the other equations, like when we had quadratic equations, we had ax squared plus bx plus c, and that a just made our graph a little tighter or a little wider. So the same thing would happen here. We're not going to do much with a values other than 1, but again, it just changes the shape a little bit. So let's dig into this excluded values piece of it a little bit more. When we're looking at excluded values, I'm going to make this just a little bit bigger. Examples of this are if I have a function where I have x plus 5 in the denominator. Again, I know that that cannot equal 0. And if x is negative 5, it would make that 0. So x can't be negative 5. In this case, x can't be 2. So if a problem were to ask you to identify the excluded values, you would actually say x equals negative 5 and x equals 2. Those are the values that are excluded. And those become the asymptotes when we start to graph. So let's look at the asymptotes a little bit more. And we're going to put this all together with a graph in just a second. The asymptotes, just like we've seen before with functions, it's where the graph of a function gets closer and closer to a line without ever touching it. So the graph of a rational function in this form has a vertical asymptote at x equals 2. So vertical up and down. I know that x cannot equal 2. So there's a line there that we call an asymptote. And then it also has a horizontal asymptote at 3, at y equals 3. And that tells us that the graph has been shifted up 3 units. So just like all the other functions where we've had an h and a k, here it's the same thing. This number right here is my h, tells me that I'm shifting 2 units to the right, and this tells me that I'm shifting up 3 units. So again, you should be really pretty comfortable with that at this point. One of the things I love about the last couple units that we study is that it really reinforces all of the things that we've done before. And the more you start to see that pattern in different settings, the more it sinks in that, in this case, the H and the K are always causing those shifts left and right, and then the shift up and down. So those are all important parts of what we need to understand to be able to graph rational functions. So when we're doing that, I've put it into steps here. The first is that we want to consider the parent function. So if I were to put a table of values with x and y, which I did yesterday in the video, and we graphed it, we would see this this shape. I guess it's kind of a lazy L shape in the corner of quadrant 1, and then a reflection in quadrant number 3. So this is the parent function of a rational function. Again, we've got an asymptote at the y-intercept, and we've got an asymptote at the x-intercept. And those asymptotes are going to shift depending on the h and the k. So the first thing that I want to keep that shape in mind, and then I want to identify and sketch the asymptotes. So let's say, for example, that my equation is y equals 1 over x minus 1 plus 2. I'm going to identify the asymptote as x equals 1. So if x equals 1, this equals 0. So that makes it an excluded value, but it also creates that asymptote at x equals 1, where my graph is going to come closer and closer to it, but it's never going to touch it because it's an excluded value. And then this plus 2 tells me that my horizontal asymptote is going to shift up from the x-axis up to y equals 2. So I'm going to sketch in those asymptotes, which I did here in red, so that then when I start to put my graph on there, I know what it's coming closer and closer to, but not ever touching. The next thing I'm going to do is I'm going to make a table, and I'm going to keep the asymptotes in mind. I don't have to have a lot of values in my table because I know that it's just going to keep getting closer and closer to that asymptote. So when I look at these asymptotes, I want to, like, if this is where it crosses, I definitely am pretty sure I'm going to have a point right here. So I want to make sure that I include 2 in my table. So if I plug 2 into my equation, I have 1 over 1 plus 2 is 3. So there's going to be my 2, 3. And then from there, I'm going to get closer and closer to the asymptote, and I'm going to get closer and closer to the asymptote. So, like, don't get hung up, especially because you're going to have fractions. Like, quickly you're going to have fractions. So don't get hung up on having too many values on the table. But you want to have a couple, so you want to see how quick, especially right in here, you want to see how tight that is against the asymptotes. But if you find this point and then this point, it's pretty easy to sketch the graph from that point. Next, you're often asked when you make a graph to identify or describe the domain and range. So we're going to use the asymptotes to define that. On the domain, all real numbers except for x can't equal 1. So again, this was the asymptote, right? So if the asymptote is x equals 1, then the domain is all real numbers except for that. And the same thing with the range. It's going to be all real numbers except for y can't equal can't equal positive 2. Okay, so that's all the new information, but let's do a couple examples to get you ready to practice. So say, for example, this is my rational function, y equals 1 over x minus 2 minus 4. One of the first things that you might be asked to do is to identify the asymptotes. So we say x can't equal 2. So the asymptote is x equal 2. That's the line. Well, we don't call this non-equal to. We're defining the line right here that the graph is never going to touch. And then this tells me that everything's going to be shifted down 4 units. So instead of having the asymptote at y equals 0, which is the x-axis, I'm shifting it down 4. So that's the y equals negative 4 is the asymptote that's horizontal. This is kind of a weird, interesting, and not so important thing, but we call 2 an excluded value because the denominator can't be 0, so x can't be 2. So we call that an excluded value, but we just call -4 an asymptote. We don't say that it's excluded because it isn't prohibited in the equation, but it is an asymptote. This to me is so inconsistent. Like, why do we not just call them both excluded values? But you know what? I'm glad I'm not an old dead guy, so we'll let them come up with that vocabulary. Not too important, so don't lose any sleep over that distinction. Second thing you might be asked is to describe the domain and range. So again, your asymptotes are going to define that for you, all real numbers except for whatever the asymptotes are. And then another thing that you might be asked to do is to compare a graph. So for example, if I gave you this function and I asked you to compare it to the parent function, you would be able to tell me that this is moving it 2 units left. And I don't know about you, but I always have a hard time thinking about, is it going left or is it going right? But I can clearly see it on this one because I know that excluded value is -2, because -2 plus 2 is 0. That's what I can't have. So therefore my asymptote is at -2, which means I've shifted that parent function 2 units to the left. And then that +3 behaves the way I think it will. It goes 3 units up. So you should be able to look at the function and compare it to the parent function by naming those shifts. And finally, you might have some word problems that include rational functions. So I did not write out the whole word problem here. It could be a variety of different things. Anytime that there's an inverse relationship, you might have a rational function. And I'll tell you a story here. I don't just have to do blah, 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 but it really could be anything. And then it gives you the function. So in this case, let's say that X is the number of students and Y is the cost. And the cost for a group of students who's planning a trip to France, it's going to, for X number of students, it's going to cost Y dollars. So there's this inverse relationship because the more students that go, the less cost it is. Because some of those kind of fixed costs that are included in a trip like that go down as you have more students. This is actually really, really common in the business world, where the cost of something is going to be decreasing the more of something that you produce, because you get some economies of scale, is what they're called in economics, that the more you produce of something, the more you're spreading kind of that fixed cost over more things. So this is really a very common relationship in the business world. Here, though, we're talking about students and we're talking about the cost, and we're wondering how many students would have to go on the trip for the cost to be $450. So that would actually be super cheap, wouldn't it? So one of the things that you might be asked to do is to graph this function. Usually if you were asked to graph it, you would be asked to graph it on a graphing calculator. We haven't done anything with graphing calculators for a while, and I know you don't have them at home, so I'm not going to ask you to do that. But the other option, and what I think most of you would probably prefer anyway, is we could graph it, or we could solve the equation. So if I want the cost to be $450, then I'm just going to solve for X. I'm going to subtract 400 from both sides. And then I'm going to multiply both sides by X plus 2. So I get 50 times X plus 2 equals 800. Then I'm going to divide by 50. You could distribute here and get 50X plus 100. But then that just gives you 2 steps. That's fine. It doesn't matter at this point, the order. So I'm going to solve the rest of that equation, and I'm going to get X equals 14 students. So again, those rational functions are super common when you're talking about the cost of something, and the more people or the more things you produce, the less cost per person or cost per item. All right, your practice tonight is on Clever. So hope that goes well for you, and let me know tomorrow. Bye.